I'd like to introduce to the stage, or welcome to the stage, Mr. Vinod Singh from Stellantis. Vinod's going to take us through how they've been adopting the desktop NVH simulator to be able to develop best-in-class NVH characteristics for Stellantis. So ladies and gentlemen, Mr. Vinod Singh. Sorry.
Thank you. So my goal today will be to tell you how we have been using it. And when I say best NVH characteristics, that does not mean that this tool guarantees that. It depends upon how you use it, and that's what my goal will be to show you to achieve that. So I have been, from last 10 years at Stellantis, I think I'm good here. Okay. I have been doing time domain transfer path analysis, which falls where you characterize the whole vehicle. The problem I always had when I showed those results in plots, sometimes, I mean, NVH people will understand, but lots of time results went to non-NVH people. And it was very hard to convince them what I'm trying to say. I would say that once we got DTS, it has given voice. I mean, anybody has some preconceived notions, I show them, whether it is good, bad, or ugly. And then that helps them determine or take their decision appropriately, I would say. So we got desktop simulator. I've been trying from last 5-6 years, I would say, after doing my transfer path analysis, but it took time. So 3 years ago, we got a simulator. And since then, we are using it for ongoing programs, existing programs, because this tool can be used to solve problems also. So, but my goal will be to give you all feel for level 1, level 2, and level 3 models, which you can use in DTS system. By the way, this level 3 model is not same as what Steve was talking about. It is, and I will go over what are the differences of these different models are. Then I will, at least 4 examples I have, which I have solved recently using DTS, and that will give you feel how are we using it. Okay, so I think that's where I think first when I said that in product development, we all know pre-concept, concept, design and prototype, and launch readiness. So we, at pre-concept level, I mean, these are the vehicles which we are trying to bring in the market after 4 or 5 years. So free drive vehicle models, where level 1 and level 2, we make sure that we benchmark, whether it is our vehicle or our competition, we create level 1 and level 2 models. Now, once that, and by the way, now we have made that thing as a process, we call it DVPNR. We do lots of testing, and we have been able to put creating testing associated with level 1 and 2. We collect the data, we create it. Now, that does not mean that it cannot be used at the later stages. It does, but we start out there. Then when we come to concept, I'm using this tool to develop NVH target setting, and I'm talking about top-down, because you want to start out somewhere with either you want to reach to your competition. So basically, you will start out with that TPA and try to put those information into DTS models. Then when we are coming into design and prototype, when design decisions are being made, NVH enablers are being developed, level 1 and 2 is limited. So we utilize level 3 because it has more information. For now, that's what I would say. And then, of course, when launch readiness is there, now you have got prototypes, you can do the same thing and you can perform lots of what-if analysis. I want to point out, up till design and prototype, that's what our goal is, that prototypes are going to be available a lot later. What can we do today? So those 3-4 blocks which you're seeing, we are working with either CA data or test data or hybrid model to answer those questions. So this slide, I personally feel that that's what we have tried to implement from last, not that it was not there, but from 3 years, I think it has become like a procedure which we are following. Now, I think little bit information on when we are trying to create DTS models. Level 1, mostly we use it for benchmarking, or knowing that where our competition is, how we stay with them. Level 2 has got capability of level 1, but at the same time, lots of time we use, or actually I would say most of the time, I'm using it for road and wind noise as a masking, because in EV applications, we may know orders, you may want to superimpose those orders with masking and see, is it going to be a problem? And if it is going to be a problem, what I can do? So that's where I'm using those, level 2. Level 3, obviously, as I said, troubleshooting. You can do what-if analysis, target cascading, and I will go in all these things a little bit more detail. And something I use quite often, powertrain swap analysis. Now, we have DTS system in our 3. We are a global company now, so we have got one in Italy, one in Brazil, and we have it here. So when we do all these things from last 3 years or 4 years, what actually Italy had it before, we can share our models very quickly. So we can share between our different regions. And drive vehicles with sound with supplier, for example, if you are getting information from your supplier and you want to include that information upfront, when vehicle program is ongoing, you can do that. So all these things, I would say that it is not 100% zero prototype, but it is helping us reduce our waiting for the mules to arrive, to know actually what I have done wrong. All these things are leading to cost saving also. So purpose is very, very clear, and it is helping us out. The biggest bang for the buck is using level 3, so I just wanted to put this slide, and actually this is the only plot or slide you will see in this presentation. So we are characterizing each source, each path, and then we are getting airborne and structure-borne contributions, and we are adding them together. And this process is repeated for all sound sources. For example, for ICE, you may have exhaust, you may have air induction system, everything will be done. It is time domain transfer path analysis, so you can play and perform what-if studies. Before we had DTS system, we could do all those things, but when you play that thing on computer or with the speakers, it is not real thing. Now we take this information, create level 3 DTS models, and people can listen. Like, I want to listen only drivers right here. Yes. Can I listen this left-hand side powertrain, left mount, structure borne only? Yes, you can. So those are the kind of things you can do, which gives a big fidelity to your model, what you have done. And if done correctly, it is telling you the right thing. Okay. I have seen this V curve since I started my career, long, long time ago. This method is really applicable. So see, when we do level 3, it has got system level information, drivers right here. You are getting subsystem level information, like powertrain, like air induction system. You can use that to develop subsystem targets. And then it is giving you component level target because it is characterizing each path And from those, you can, so it has got all those three things, and that's what exactly we are using. And how I am developing those targets, I think this flow chart gives you a little bit of idea. So we are starting out with overall and orders at DRE. You can, and they are structure-bound and airborne separate. You can define this thing as a subject system target. Then I am showing you with two blocks contributions, for example, powertrain. Structure and airborne contribution, because it is just coming from powertrain. Isolation information is also available. Along with that, transfer paths are available. And you can know dynamic forces from mounts also. So see, that's, so you can provide that vehicle integration, those first two blocks, go meet this. Then at component level, those people can go acoustic side, for example. You can do sound power, or you can, or volume velocity. You can convert it into sound pressure also. I think that's a little bit of question mark. On acceleration side, actually, you have all information to really go. If somebody wants to know what should be my excursion, at least on active side, you can even produce that. So this is the flow chart generally, I am using from that level 3 information and giving this cascading information to different subsystem and component. So that gives you a feel for that, how you can use this. Now, this is powertrain swap analysis. So when you are thinking of developing vehicle for best NVH characteristics, you may have got some vehicle in mind whose paths, for example, are great. You may want to use your powertrain, and you may want to see if I put this powertrain in this vehicle, how it will sound. You can do this thing easily. I would not say easily. It is a very involved process, but basically you have to have a few things. You have to have target vehicle. Your path has been characterized nicely. Source, intended powertrain, you will put it. And using that information, you can predict how that powertrain will sound in that particular vehicle. Now, it will just not tell you only how it will sound. You can, again, go back and look at all paths, all contributions, and make your decisions accordingly to achieve that goal. Having showed you this, now I'll give you some examples which came to me, which I could not answer before. Now I'm able to answer those things a lot quicker. So request was, we were working on some EV vehicle, simulate the EDM noise in existing DTS model and perform a listening session. Request was because they were not sure how this thing is going to sound like. So obviously there were some tasks which you will show you that we started out with CA information. So existing DTS model was used to include EDM orders, and first that information came from CA. We did that demonstrations. I think it went pretty well. By the way, for masking, we used road and wind noise, which we already had from our previous studies. Later on, the same EDM was being tested in Italy, and I got those orders in the lab setup, those orders. Then I simulated that into it. It was all ongoing. Another thing, we simulated was lots of time people who work in EV industry, or EV powertrain. Front end, there are two EDMs, and it depends upon, if you keep them at same RPM, running at the same, and gears are kind of very close, it can lead to modulations. And that phenomena I was able to demonstrate very easily. And then we found the solution, how much separation it should have so that it will not create that problem when we get the mules. So I think I felt that, this was a very good way of looking at problem which should not happen. So I'm just showing you the results here. EDM noise was not completely masked. They clearly saw that. And obviously, that information was used to see what we can do to the path or source. And it is an ongoing process, but at least we were able to see that, yes, this will be a problem. So again, usage. By the way, because I use CA data and test data also later on, so we certainly helped in correlating our CA model, which was not too far, by the way. I think prediction was very close, but it was not exactly same. So they are using that information for CA correlation work. Okay, so that was one project. This project is still right now ongoing. Actually, this morning, before, I was supposed to come here at 8 o'clock. Yesterday, manager for whom I am doing this analysis, he calls me and he says that, you need to come today. You have two choices, 8 to 9 or 10 to 11. I said, I'll come at 8 o'clock. So I just did the demonstration before coming here. Here is the issue. They had, so this is also an upcoming program. They were not meeting criteria, and obviously CA is developing solutions. But they had no way of knowing how this is going to sound in the vehicle. So obviously, I helped them do this thing. So again, I'm not going to go, task performed was exactly same. You have to start out with the target vehicle. We knew exactly what all those things are. I was able to take that CA information in the form of ratios that between two designs, like or 5 designs you have, and we simulated all those things, and there was a demonstration. Obviously, so when we went through that thing, design number 1 was POR. They were going with this thing. We found that that's a design you do not want to put in the vehicle. Solution number 5 was the best design. Now, today's demonstration was number 5 is going to cost X dollar more. Nobody wants to spend. Everybody wants best characteristics, but nobody wants to spend money. We brought people who are making those decisions that no, we cannot spend that money. They heard it today. Now, I will find out after a few days, whether whatever decision they will take. Again, my job is to provide that correct information, but without this tool, I think I would have not been able to tell them with confidence, and which they can listen. So, all right. So that was example for this project. This was like, first one, basically, this was, they knew couple of orders, they are not meeting the target, and lots of time in practicality is that, sometimes, they may want you to relax those targets, but because we had this tool, they wanted to really know if we do not meet, really what it will do. Is it really going to create a big problem? So again, simulated that thing in a vehicle and superimpose those orders. And I think result was if I will pose an issue, and we were, and not only that, we were able to show that how much reduction you really need to make this acceptable. So we are not just saying, okay, you're not meeting the target, okay, we are exactly telling what you need to do to meet those targets. So again, this was also, I felt that I would have not been able to answer this question without this tool. And the last one is, again, very recently, they are trying in a new vehicle program, they are trying to move the snorkel location at a different place. And obviously, that is going to create, snorkel is the biggest noise contributors in some vehicle. In some vehicles it is not. We were able to evaluate and tell them that this particular location is certainly going to cause problem. And I'm talking about 4 to 5 dB difference at driver's right here. So obviously, they have got some work cut out for them. They just cannot, without this tool, I think maybe they would have moved it. I don't know. So at least it is letting them think that they have to do something. Okay, so this is where we are. So I think first 2 slides are what I have, is we are running any vehicle condition, and people who are familiar with, USO cycle and all those things, I call it whatever work I have presented. If people can listen, I will call it passenger seat evaluation. You do not have feel of a vehicle. And what that happens, and let me tell you one drawback which I have come across with people who could hear. It is very different when you sit in front of a simulator because you are not feeling tactile input. So sometimes people feel that it is louder than what they generally experience, which is not true. It is because of that. So to fill that gap, we are trying to see, can we do driver seat evaluation? And I'm not going to go too much detail. This is a still ongoing thing. We are going to use something DTS plugin, they call it, where engine RPM, torque, vehicle speed, gear is input, and steering angle, throttle, brake, information comes out. So they can really feel along with sound. And I think that will also enhance our capability in that area.